Okay, so let's talk about two of the most important protocols that we can use for IoT today. And these are CoAP and MQTT, and go into more details about how these protocols work and what is their scope and what we can actually achieve with them. So first of them is CoAP. CoAP comes from a constrained application protocol, and it's a protocol designed for this paradigm of Internet of Things, where let's say you have a difference or a clear distinction between how you do things M to M. M to M is machine to machine. So this was the original paradigm of how things were done in automation, in industrial and home applications over the past, I don't know, maybe in the 90s and the early 2000s, where you had kind of like independent systems for automation that you would connect to a certain application over a network that might have been the internet or might have been something else. So you had, let's say, different types of applications that will connect to different types of automation solutions, whether in your home, whether in your factory, whether in your car, and so on. So these would rarely communicate with each other, and these would rarely be aggregated into a, let's say, single front end that the user could see. Now, when you have the Internet of Things paradigm, then the idea comes to actually join all these applications, be it industrial, be it home automation, be it something else, through a series of common protocols that are standardized. So CoAP is one of those protocols that has a, let's say, very ambitious goal of actually unifying different types of applications. The communication is done through the internet, of course, and then the front end part might be separate, might be dedicated to a certain type of application, or might be a common front end for multiple types of automation that you have installed in different locations. So it's what CoAP does and what MQTT does in the same manner is to offer you a lot more flexibility and a lot more compatibility with different types of applications. So when you're looking at, drawing a line between M to M, so machine to machine, classical automation style projects and IoT in general, uh, the main difference is that in M to M you have simple device to device communication. You have an embedded software at the client side that actually runs some commands to the automation itself. With IoT, the scale is much larger, and you usually have a one-it-all approach. You would like to automate as much as possible. You would like to have automation ubiquitous in your environment. Uh, in terms of standards, of course, M2M has some isolated standards and isolated devices or systems that don't usually work together to achieve a greater purpose. You usually have a very focused approach of automating only one tiny part of your system. With the IoT paradigm, you integrate these devices together. You merge sometimes data, you integrate different applications, and you work across varying standards with some sort of protocol stack that unifies everything. M2M has limited scalability options because of this. So because of having isolated systems, whereas IoT is inherently more scalable because of that. Uh, of course, for connectivity, they could use the internet, both of them. There's no distinction here. But because of, let's say, the history of M2M, and how it has developed maybe before the widespread availability of the internet, you usually have wired dedicated networks or even cellular networks. So maybe no 4G or 5G data networks to actually send your information, but simple commands that can be sent through a cellular network or even an SMS service. Um, Now, IoT is becoming the state-of-the-art approach with every automation system. It's even sharing some wide-scale adoption with industrial applications, but it's still not gained let's say considerable foothold in industrial applications just because M2M is still prevalent here. Now, what does CoAP offer as a protocol? Well, it's a protocol with very extensible set of features. So it offers device management. It offers possibility for the user to discover uh, certain devices, and more than that, discover devices, settings, and parameters, and allow you to actually communicate with a certain device type, or send individual commands, or send messages that are broadcasted to multiple devices at the same time. It's it works like a web protocol, so you can actually use it freely over the internet. It's got an asynchronous message exchange scheme, which offers a very low overhead of communication. So it's much more efficient than HTTP, for example, in that regard. It's got a very similar scheme to HTTP in that you have a URI and content type support. So this is pretty much similar or even copied from HTTP, and it's got proxy and caching capabilities. So you can actually proxy through a CoAP network, or you can cache some data in a certain device from another CoAP network. Would you use CoAP? Well, you can use CoAP when you have very simple hardware that you cannot actually run HTTP or TLS on. So there's let's say not enough capabilities to actually run more complex protocol like HTTP. Be it you don't have a lot of memory, or you don't have a lot of processing power to actually achieve this. CoAP can come to your rescue. It also has a secure layer of communication created by DTLS, and can practically do the same thing as HTTP. I mean, you have the same methods, the same basic methods that HTTP offers, such as get, post, put, and delete. And you can use these to actually transfer data between devices in the network. So very low power, low capability devices that can actually employ CoAP to communicate within the network. It's also very efficient in terms of energy consumption. So when you have devices that use batteries to power themselves, HTTP is not oriented towards energy efficiency, not at all. So you can run CoAP, and this will definitely improve the battery performance when compared to HTTP. You can have a connection through CoAP that uses UDP as a transport layer protocol and not TCP/IP. Uh, because it's stateless, so CoAP is definitely stateless in this regard. You do not need to have a lot of communication overhead at some point. Um, you need, though, a subscription. So you cannot uh, when you need a subscription, or you cannot run MQTT or HTTP, CoAP is a solution when that is the case, and we'll see what the subscription means when we talk more about MQTT. So this is how a structure of a CoAP network actually looks like. So you can have different nodes that transfer CoAP messages within their sensor network, so to speak. So you have these constrained devices that maybe are powered through battery, and they're very low in capabilities of memory and processing power. And then you can also transfer messages directly to the internet, to a server. So you can have an architecture where you have these devices transferring CoAP messages to a proxy that actually translate these messages into HTTP, and this is then sent over the internet to the server, or you can send directly messages through the internet to a server using CoAP. So you eliminate the need of a gateway or a proxy to your network. So as a standard, it's open. It uses UDP as a main transfer protocol, but it can also use SMS, for example. So short message service as a method of transferring messages, or it has a support for TCP built in. It's got ETLS as a security layer. Um, it's got built-in discovery, so you don't need to actually know all the specifics of the devices that are in the network. You just query a node to actually, and the node will send you its capabilities. So whenever you were looking at how messages are handled through such a network, you usually go from web applications that transfer data over the internet, where packages usually are in the terms of thousands of bytes. So a packet might contain some high-level web object data, and then it has the lower layer hypertext transport protocol, TLS, TCP, and IP data. So this whenever you're packing this data, it's usually in the terms of thousands of bytes. This cannot be actually transferred in a very constrained network because of its size. So what you usually do is you actually proxy this information, and you actually get rid of a lot of the, let's say, overhead that these messages have, to actually transfer it to maybe a packet size of hundreds of bytes. So you have a binary web object. You actually encrypt the data here, where you compress it, because the object itself is, let's say, a plain text, or it could be a markup language specified object. And you can actually store it more optimally in binary encoding. So this saves you a lot of space for your packet. Then you have some CoAP data, DTLS, UDP data, of course, for the security part and the transport product, and then the IP. The IP part is pretty much unchanged. Now, if you want to transfer it to a sensor network, then you can compress it even further to maybe tens of bytes by getting rid of the IP part and replacing it with 6LoWPAN as an adaptation layer, as we discussed in the previous lectures. So this is how pretty much messages are being handled in such a network, from constrained devices with very limited power and processing capabilities that you would need for them to handle messages that are very tiny in size, so maybe tens of bytes, to let's say proxies or gateways that handle capabilities of let's say more than hundreds of bytes, to messages into internet proper. So before talking about the particularities of CoAP and the specifics of it, let's talk a bit about the web and REST. Okay, so web architecture usually is, let's say, comprised of servers and clients. This is, let's say, a very standard way of sending data through the internet, where you have, let's say, multiple servers that can connect to different clients. One client can connect to one or multiple such servers. So it's a pretty standard architecture of how things and how information is actually sent through the internet. Now, usually, whenever you are accessing content over the internet, you use a web naming scheme. In this web naming scheme, you have, let's say, a domain name, which is, the www something. It's the physical server address where your website is hosted, basically. So that's the web address. And then you might follow that domain name with an URI. It's an identifier, universal resource identifier, which maps to particular files that are contained in that server. So you can actually specify which files you would like to access, and then for those files you would also access a query string. So you could have this query string that would actually specify a part of a GET request for an HTTP message. So you easily pass in values to customize the output that you would require from this resource here. Okay, for example, and I'm sorry for the bad compression here, this could be a web naming scheme. For example, you could use HTTPS. This is a secured HTTP transfer method, and then you have some user info. For example, you might have some user info and then you have the domain name. You could also specify the port for which you are connecting, and then you have the path to, I guess, your file or your files in the server, and then you have a query and then a fragment. So why am I specifying this? Because CoAP uses a very similar method of locating resources. So whenever you send such URLs through your browser to the internet, what usually happens is a URL resolution scheme. So you have different parts of your URL which are being parsed, and then these specify different parameters of communication at different levels in your stack layer. So for example, example.org, this one is the URL, and this goes through DNS to actually specify an IP address. So DNS will actually give you an IP address for your URL. And then you have the port. The port is relevant through, let's say, the TCP part of your stack, because it specifies, whether you're using a certain port or another for communication. And then the other, let's say, parts would actually, or the query or the files would actually point to a resource, so higher in the protocol stack. Uh, Things are done usually through HTTP requests. So whenever you would like to actually access some data, you have a simple TCP handshake between a client and the server. So kind of like a SYN and a SYNAC. This is usually handled in very short time. And afterwards, you would get basically the HTTP arbitration. So you would get uh, get method from the client to the server, and then the server prepares the HTML response. And after a while, it would send you the HTML response. And then usually the communication would close. So there's not a lot of states here for the simple query for an HTTP request. It could be a get, it could be a post, it could be something else. I mean, it doesn't need to be particularly get here. This is how things are handled whenever you are querying some sort of resource, some sort of website from the internet. Now, there are two web paradigms that actually could be employed to get information, and they both work over the internet. One is representational state transfer, so REST in short, as a resource. The other one is SOAP as a service. Both of them actually work at a higher level in the same fashion, but CoAP uses a REST scheme in which a query is actually specified through some sort of XML scheme, something like this. So whenever you would like to query, for example, temperature from a given, I don't know, sensor, you would actually have a get command from the sensor, and you would actually get a response in an XML scheme. So this is how a REST request, not only over CoAP, but a general REST request would look like. So, for example, you have a client. The client would have a get method of, let's say, temperature. Temperature is the resource we would like to query, and the server would actually send back the temperature value appended to a message that also contains a state of the message. So you get a confirmation code, and it's identical to the confirmation code from HTTP. So 200 OK. You get again a specifier of how the information is encoded. This is plain text, and then the actual information. So 22.5 degrees centigrade, you would actually get back from the server as a response. So this is basically how CoAP works as well. And now let's dive deeper into what CoAP can actually achieve. And we have different design requirements for our CoAP network if we are going to be able to actually support this type of architecture in which we have different constraint devices here. So as a first requirement, it will have to work with devices that have very limited flash memory or very limited RAM memory. So limited processing power and limited memory footprint. Another request would be to actually work within constrained networks. And constrained networks are usually devices that are battery powered, so they don't have a lot of energy resources available to them. And the radio environment that they're communicating in might be a crowded one. So you're going to have a lot of packet loss. You're going to have a lot of noise affecting your communication. Then, in order to conserve energy, you would actually employ some duty cycling scheme to your devices. So the devices don't always communicate. They are not always available for messages. So you will have nodes that are waking up and then sending some messages and then going back to sleep. So a very low power mode in which they're not available for communication. And the protocol would have to work in this fashion or over these types of networks. Then you'd have some sort of capabilities of caching information at a proxy, which is let's say a more able device. So it has, let's say, ample amounts of memory, more memory than the constrained devices themselves. So it can store some information temporarily from the devices, or you can store commands and send them to the devices whenever these devices actually wake up. You'll have to have different types of resource manipulation, discovery, ways of subscribing and notification for these devices. So sort of a method in which you could actually achieve this. The proxy itself would have to be able to map these CoAP responses to HTTP and backwards whenever you actually translate messages in this fashion. And then it'll have to be, multicast, so you'd have to maybe communicate in some instances from one node to multiple nodes within the network. Ideally, you would need to be, reliable in communication and have a very low latency in your communication. Again, you would like to be stateless here because of the different constraint of the devices. They will not always be able to communicate with you. So a simple scheme of sending a message and then getting a response would be ideal for these type of networks. So you would prefer UDP as a transport protocol because it's stateless. And then different requests for manageability of the network that you can actually employ. So this is how the network looks like for CoAP. And I just want to make sure that we are in what CoAP is and what CoAP is not. CoAP is a very efficient RESTful protocol. You can actually employ it in ideal situation. It works with constrained devices and constrained networks that are very limited in bandwidth, very limited in processing power, very limited in battery capabilities. You can actually apply it to M2M applications. So you can switch to a paradigm where you have total decoupling between different applications, and you only have let's say a single, let's say, stream of data flowing from your application to a certain visualization or front end app. And it's easy to proxy to and from HTTP. So you can translate easily to and from HTTP with CoAP. You cannot achieve with CoAP, however, a general replacement of HTTP. So you have only a reduced set of features of HTTP in CoAP, just because the network that CoAP is designed to work over is limited in capabilities. Again, it might look like CoAP is being very similar to HTTP, achieves actually an HTTP compression scheme. It does not. What you actually have in CoAP are messages that are very similar to HTTP, but at let's say base level, it's very different from how HTTP works. And it's not restricted to, let's say, isolated automation network. It can work over the whole internet. So you can even send packages between PCs, for example, using CoAP. Now, as a features, it's an embedded web transfer protocol, so it's been standardized, and you can use it if your browser supports it. There are even plugins for Chrome or for Firefox that you can actually install, and you can use CoAP to transfer your data the same fashion you use HTTP to transfer data through your browser. So you have a scheme like CoAP like this. It's an asynchronous transaction model, so you don't need kind of like synchronization between different devices in your network. UDP, you get these, let's say, standard methods, the four ones that are basic for HTTP as well. You've got the scheme in which you have URI support, so CoAP can work again with URIs, a very similar fashion to HTTP. But dissimilar from HTTP, it's got a very tiny overhead of communication. So, for example, you only need a 4-byte header for CoAP packages within the network. You've got DTLS as a scheme for security, and built-in discovery, observation, block transfer, and so on. Let's talk a bit more about what these mean. At the transactional model, CoAP defines UDP binding, so you can transport data over UDP with DTLS as a security layer, or you can send CoAP messages over SMS or even TCP if necessary. But most of the time, the applications that we are using in IoT, they use a UDP binding. So, of course, if the applications are remote, you can use an SMS service for this. And it works very well over it. It's got a base messaging scheme in which there's a simple message exchange between different endpoints. And you have simple acknowledgements or resets that are being sent in reply to your message. And it's got a semantic that is REST. You've got a type of request response scheme that is in terms of method, code, options, and so on. They are very in tune with the REST philosophy. Now, looking at the message header, you have this this very simple 4-byte header here that comprises a version field, a 2-bit unsigned integer indicating the version of the CoAP protocol. You add T here, another 2-bit integer indicating the message type might be confirmable or non-confirmable. You've got a token, a 4-bit token that is applied to every message in order to sorry, the token is 32 bits, but the token length is 4-bit in length. And this token is unique to a certain message, and usually when it's a request response type of interaction, the request has the same token as the response, so it can be easily identified within the devices. You've got the code. This is the code of the response, and it's got 8 bits in length, and then you got the message ID. Again, 16 bits for a message ID. Then it follows the token, options, and the payload. If you have options and payload, so these last two are optional within the message itself. How does it look like? So let's presume we have a client and the server. They both operate over CoAP. So the client, for example, might send a query, and you can actually query kind of like a get message for a resource called light, and you apply a token to this message. This could be the token AF5, for example. So whenever the server responds to this particular query, it would send an acknowledge with the same token, and then a code, a response code, in this case 205, and then the content of the message itself. So it's a very simple scheme of sending a query and then getting a reply. And this is all. I mean, it closes like this. You don't have another state or another exchange of messages happening within a network. So whenever you have packet loss, for example, a packet does not reach the server, or for some reason, again, the response from the server does not reach the client, you have a retransmit scheme. And the server does not know actually if the message was captured by the client, or does not know if the client has sent a message in the first place. So it's the client's job to actually resend the message. So whenever you don't have let's say a message coming in an available time, you have a timeout period attached to each message. You can choose as a client to retransmit the same message, and hopefully this time it will get through, and you will get a response from the server. So you can actually use this to communicate and to deal with packet loss, or you can actually have the situation in which the server can separate the response from the query in time. Let's say that the query takes too much time to execute on the server, and the server cannot actually give you a response in the given time. So the timeout of the client would expire. What the server does then is to send a simple acknowledge message without a payload. It just contains the token of the communication. And as soon as the response is available, the server would send a new confirmable message to the client containing the response. So this time, the client doesn't have to query the server anymore. The server will send the message whenever it's available, and then the client will actually acknowledge this message. So for example, you would query light here, and light, I don't know, takes too much time, so to speak. Then the server will actually acknowledge with a simple message, and then whenever that resource is available, it will send another message with the content of the response, and the client will acknowledge. Now, bits and bytes, how one message, for example, this message between the client and the server. So connection message with this token and method and so on is separated between different fields of the CoAP message. So you see here the different bits and bytes that are being actually contained in the CoAP message, and also in the server response. Okay, any questions so far? So let's talk more about caching then, because CoAP includes a very simple caching model in which you can actually store information on other devices than their originating source. So you have this model where you can actually specify the data freshness. So you can append the max age option to indicate the lifetime of the cache. So after a time being stored in a cache, the data would expire. You can also have a validation model, and the proxy often supports caching. So whenever you have a proxy within your network from HTTP to CoAP and backwards, the proxy can support this caching model in this fashion here. So let's say, for example, you have a CoAP network and you have a CoAP server in the network that exchanges CoAP messages to a proxy, and the proxy translates these messages to HTTP messages that are sent to an HTTP client. So for example, the client would query resource from the CoAP server. This resource is light, so it would send an HTTP GET to the proxy. What a proxy does then is to actually translate this HTTP GET into a CoAP GET for the same resource. The CoAP server will reply with the value of the light resource and a max age of, let's say, 30 seconds. So uh, this response of this resource, this value of this resource will be available at the proxy uh, and will not expire for the next 30 seconds. So in this interaction here, the proxy will reply directly to the HTTP client with a 200 OK HTTP message containing the light value. And then whenever the HTTP client queries again the same value within this window of 30 seconds, then the proxy will not query anymore the CoAP server. It will send out the same message with the same value to whatever client it's got connected on the HTTP network. After the expiration period, the proxy will send again a query to the CoAP server in the network. So it's a scheme where you can actually cache some data here, and you can actually save some network traffic within the network for parameters that don't vary that much in time. So light, for example, temperature and so on, they might not vary very much during a 30-second time window, or even more. I mean, you can actually modify this parameter here to be as much as you like. You also have observation as a scheme. So you can observe, let's say, a certain parameter. And you can do that in a CoAP network when you have a client querying parameters such as light, and then you basically subscribe to this parameter with an observed type of message. So what this does is the server will send you first an acknowledge with, let's say, the first value for the light, and then the client does not have to send repeated queries to the server. The server will send repeated responses to the client with new values for this resource, light here. So whenever light changes, the server will send new values automatically, kind of like a subscription service to the client. So you can have this functionality as well. You see that token here is shared between all of the server's responses, future responses, and you have kind of like a different sequence number for the observed field here that shows you actually how many messages with that parameter have been sent. So 27, 28, whatever, 29, you just increment whenever you you send a new message. The client simply acknowledges receiving these observation messages. You can also support block transfer through CoAP. So you have this scheme, for example, where a resource is has a lot of bytes in size, so you can't actually send this entire resource over the CoAP network through a single packet. So what you do actually is you split the resource in individual blocks of 1024 bytes that you can send through messages to the CoAP client. So you split it, you send it to the client, and the client assembles the message, the original 4K message. So you can send let's say files that are big in size, let's say kilobytes in size, through the network through this block transfer scheme. Now, if you want to get started with CoAP, if you want to test CoAP application and see how it runs on your ESP32 boards, there are different open source implementations which are available to you. For example, Mbed, so a series of microprocessors from NXP, includes CoAP support. You have on the browser side of things, you have different plugins that you can use. You have a Java CoAP library as well that you can use to actually implement CoAP at on your PC. You have C CoAP libraries which are open source, and you can definitely use them in your embedded applications. libcoap, jcoap, RPM as well. I've included a few links here that you can actually use. And then there are the plugins for browsers. So Firefox, for example, has a CoAP plugin. It's called Copper. Chrome also has a CoAP plugin. You can install it through their service, their plugin service. Wireshark has a CoAP support for packets, and you can actually see the packets and the messages. And because it's very simple and stateless, you can implement CoAP yourself. It's not that hard to actually implement, and you can be very selective in terms of what parts of CoAP you can implement. So for very constrained devices such as Arduinos, you can even go so far as implement maybe a tiny part of CoAP. So not the entire support for block transfer, for example, or subscribing, observation type, things like this. Now, this is kind of like, the architecture of CoAP. Now, moving forward, we're going to talk about a different type of protocol. It's called MQTT. And this one, has a bit of a different scheme of transferring messages than CoAP. So you've got, just like CoAP, you've got multiple clients, but the information is sent in a publish-subscribe fashion, and you use actually brokers instead of servers to connect to and to relay your information to. So let's talk a bit more about MQTT as a protocol. MQTT stands for Message Queuing Telemetry Transport. It's Internet of Things Connectivity Protocol, which is also very powerful. It was invented by two engineers, so one from IBM and another one from Eurotech in 1999. So it's a very recent protocol, so to speak. It's got 23 years only. It's a standard, so it's been standardized, and you can see the ISO standard number here. It's public. It's got a royalty-free license. You can use it pretty much virtually anywhere, and it's widespread use by different companies, especially in their cloud and web services applications. So Microsoft Azure, Amazon Web Services, even Facebook Messenger uses it as a transport method for their messages. As a feature, it's got a very small code footprint. So it's ideal, again, just as CoAP was, if the processor and memory resources are very limited. And again, you can transport messages through a network which has a high packet loss rate, and you have a very low bandwidth of communication between different devices in the network. It's got a message exchange pattern that uses this publish subscribe scheme. And apart from this, and very different from CoAP, it uses TCP/IP as a communication model. So it works on top of TCP/IP. Another interesting feature of MQTT is that it offers quality of service levels. So you can have at most once, at least once, and exactly once at different QoS levels. There are client libraries available in different languages, C, C++, Java, you name it. It's available for Android, it's available for Arduino, and we're going to make a short demo after this this lecture in which we will actually see it running on ESP32. It's got security as well. It's authentication using name, password, and encryption using secure socket layer. And it's got support for persistent messages that are stored on the broker. So let's say a similar scheme to what CoAP did with cacheable messages. You can have persistent messages which are stored at the broker level and sent through the network repeatedly. Applications are kind of the same as CoAP, so you can use it in different sorts of IoT scenarios, from home automation, healthcare, industrial automation, automotive, mobile phone apps, and general IoT applications. This publish subscribe method uses basically multiple clients that connect to a single broker. So a client can connect to one broker or to multiple brokers, and you can subscribe to different topics that they are interested in. So for example, if I want to query, let's say, temperature from, I don't know, maybe 10 nodes within my application, I can subscribe to a broker to the topic of temperature that is shared by these 10 nodes. Also, when you want to publish, clients can connect to the broker and publish their messages to different topics. So communication between, let's say, different devices within the network is handled through the broker. The broker is the central point of information exchange. Topics are usually treated hierarchical. So you have a slash as a separator, and this constitutes like a kind of like a hierarchy in which you you can have multiple sensor devices that publish temperature readings on the particular topic. So you can have sensors, for example, slash device name, and this is unique to each device, slash temperature, and this is commonly shared between these devices. And then you have, again, node ID, which is unique to all devices there. So you can query the temperature from node 1, 2, 4, 5, and so on, using this the scheme of topic specification. Clients, they can receive messages by creating subscriptions, and the subscription may be on a very explicit topic, in which only messages to that topic will be received, or it may include wildcards. So, for example, you have two wildcards available, plus and or hashtag, that will actually specify if you want to have a single topic to be received, or you can have multiple topics here. Also, MQTT clients can register a custom last will testament message that can be sent by the broker if they disconnect. So whenever an MQTT client actually, I don't know, maybe its battery depletes or its connection becomes unstable, you can leave at the broker kind of like a last will testament message to actually signal that you are not available anymore. Or you can signal the, I don't know, maybe the last recorded data that you measured. You have this publish subscribe scheme in which this is an example. You have, let's say, 3 clients which are subscribers to a single topic. This topic is temperature, and you've got this client which acts as a publisher. So the client has a temperature sensor on board, and it publishes temperature sensor data to this broker here. And then you have these 3 clients here that can subscribe to the same broker, and they can query the temperature value that this client here publishes. And again, this client here can also subscribe to a different topic, which maybe another client here can actually publish to the broker. So it works both ways. You have topics or subscriptions that are messages published to topics, and clients, they can subscribe to a topic or a set of related topics. And then you have this publish subscribe method in which clients can subscribe to topics or publish to topics. So it works both ways. This is how request response scheme actually works within MQTT. So first you have the client that subscribes to a certain topic. So for example, let's say that this is a topic that you can subscribe to. You can actually the client, the server actually can give you a subscription to a topic which is function XYZ request /plus. Plus is a wildcard here, so you have all the IDs. You can publish a certain topic, so you can actually go to request /ID, and you can have different interactions, such as receiving and retrieving and processing different functions at the server. We'll go through for the example, and you will actually see what these actually mean when we have the demonstration. So as I told you, we have 3 QoS levels in MQTT, something which CoAP does not have. 0 is at most once. So this is a best effort transmission of packets. You don't require an acknowledge whenever you send a packet. So this is the lowest level of quality of service. 1 is at least once. You have an ACK response whenever you send a message, and you retransmit if an ACK is not received. And you have an exactly once, in which you have, let's say, more intricate scheme of a handshake between the client and the broker. You have it here. You have a request to send, a publish, and then you have the clear to send, you have a message, and then an acknowledge. You can also retain messages. So the server keeps messages after sending them to all subscribers, and new subscribers can get the retained messages. So kind of like a caching scheme. Different features for MQTT also include clean sessions and durable connections, sorry. What does that mean? Well, at connection setup, you have a clean session flag. That means that all subscriptions are removed on disconnect. Otherwise, subscriptions remain in effect after disconnection. And any subsequent messages with high QoS, they are stored for delivery after reconnection. You can have this will scheme, last will and testament connection that no longer is available for a client. A client can previously inform that should it be disconnected, then the broker could send a particular message, and you can alarm the client or different subscribers if a certain client loses a connection. You have periodic keep alive messages to actually check if a client is still alive, and this work in connection with this will scheme. And you have topic trees, topics that are organized as trees using the / character. So you have these wildcards, hashtag matches all sublevels, plus matches only one sublevel in the scheme. Now we're going to follow with an MQTT demonstration of how this works, in which we're going to have the ESP32 board or your boards connected to an MQTT service. So you have this broker, and we're going to use Adafruit.io as an MQTT broker to actually connect to the board and publish and subscribe to different topics. We can also use clients. So you can use a desktop MQTT client to actually connect to the broker itself and send information to the broker that will then be sent to the board. Or you can even use a mobile MQTT client on your phone to actually query the board and to actually send commands to the board. But let's take a short break, maybe 15 minutes, and we'll be back after the break with the demo, okay?
Okay.
Any questions so far about MQTT and CoAP?
From my side, no.
Okay, thanks then. Let's take a break and then we'll be back.